Our next speaker is a late substitution. Joe Licken was unable to make it here because of the Lufthansa strike. And fortunately, we have Maria Spiropulu, who courageously has stepped in to tell us about the implications of the Higgs boson.
Okay, so I am going to be talking about the future of the Higgs boson, which, of course, when I gave a colloquium, some undergraduate students said, but we read the Higgs boson does not have a future, it decays in yoctoseconds, so what is this all about? So the title comes from a paper we wrote with Joe, who unfortunately is not here to talk to you today, but the paper we wrote about the future of the Higgs boson mainly concentrated on connecting this really paramount discovery to the future of high-energy physics, as well as connecting the ideas with other paths of physics, with other sectors of physics. Now, there was in 1996 when I took some when I was in a summer school. Eric Larson from now Amsterdam, but he was a postdoc then at Fermi Lab. He told us that when the Higgs boson is discovered, do not just say you discovered another particle. It is a way of seeing the universe in a new radical way, and this was encapsulated indeed by the fact that when the Higgs discovery came about, as John mentioned, there was a huge interest from the people and the press and all other scientists as well. And this was just one example. He showed you many more. This is the paper I was talking about. It's called The Future of the Higgs Boson, and it starts with a little Higgs history, namely let me just get this. Okay, I can't get this to work, so let me try this. So this is from the lecture of Nambu, his Nobel lecture, given by Lasigno, in fact, on spontaneous symmetry breaking in particle physics, a case of cross-fertilization. And the main point there was the Higgs boson idea came about as an application of condensed matter idea to particle physics. And this may have been surprising to some people, but indeed the difference was that instead of having a many-body system in condensed matter physics, you have a many-body system of the quantum vacuum. In other words, the quantum vacuum is and can be seen as an n-body system, and it's a medium. This is important because when we discuss symmetry breaking, which is an obvious thing, it is only obvious if you think about it as such. Namely an n-body system. And Nambu pointed out about symmetry breaking, different kinds of symmetry breaking in different physical systems, so ferromagnets with spin waves, crystal with phonons, superconductors with Cooper pairs, or the heavy photon. So here is the Goldstone Mexican hat. So it's Goldstone's Mexican hat, and I saw the paper actually in a typewriter of Goldstone from 1960. He published it in Nuevo Chimento in 1961, and he had the first hand-sketched Mexican hat potential, and he was studying symmetry breaking in superconductors. So the potential is this one. Everybody has seen that, and the potential represents the energetics of a scalar field that turns itself on. And then we usually claim that we drop here at the trough. We have the phase modes, and the size of the trough here is the Higgs boson, and we call that spontaneous symmetry breaking, and we say it's obvious, but of course, again, undergraduates will tell you it's not so obvious at all, because if you look at the double well potential that we do in physics, the actual ground state is the superposition that preserves the symmetry. It doesn't break the symmetry. So what's the difference? And the difference is indeed the fact that the vacuum, the quantum vacuum, can be seen is an n-body system of different degenerate states. It's quantum mechanics, in other words. So Phil Anderson wrote this first in 1972 in an article called More is Different, where spontaneous symmetry breaking was mentioned as a property and discussed as a property of large systems. And I think the insight was very, very useful. Now we come to the actual Higgs boson particle. It was Higgs with Brut, Engler, Guralnik, Hagen, and Keeble. And now, let's see, this is Guralnik, this is Hagen, and this is Keeble. And Higgs when he was very young, and Engler and Brut. And Higgs and Engler got the Nobel Prize. And we talk now about the fundamental scalar field with self-interactions, the Higgs. It causes spontaneous symmetry breaking. It's global symmetry breaking of the quantum vacuum. It gives gauge bosons the mass through this famous eating mechanism. In other words, the gauge boson eats the Goldstone bosons, and one is left, while respecting the delicate choreography of gauge symmetry and Lorentz invariance. This was explained by Higgs himself at the Nobel Prize to Fabiola, Marcella, and Lars here. And so he explains that if you started with a complex scalar field, there will be a neutral massive boson left over, and eventually you get a trip to Stockholm, and you write a message to Joe and Fabiola thanking them on August 30 after the announcement of the Higgs. So since this is about the mass we're talking about now, let's go and clarify a couple of things. Elementary particles, when we write down the free and the interaction part in the Lagrangian of the Standard Model before the Higgs, do not have naturally a mass. But they can acquire a mass through dynamics. So for gauge boson, this is the Higgs mechanism. That's for the doubly using the Z's. For the quarks and the charged leptons, there is interactions with the Higgs field that gives them mass. But it's tricky. And the mass generation for diverse flavors, in other words, why each of the flavors have different masses, is also a big mystery. So here is a table of the quarks and leptons in the Standard Model. And it shows you in a way how the different particles have different masses, the patterns of which, why the masses are so different is unknown. And also we have, for the quark sector, we have a way of describing their interactions and describing the amount of CP violation that we have in this sector. And the Higgs plays a role here, but in the entire picture of, for example, CP violation in the lepton sector, we're still behind, and we need to understand if there's something that we're missing. Perhaps it's an extended Higgs sector that we're missing. So the flavor questions that come about with regards to also the Higgs discovery is what are the dynamical origins of fermion masses and mixings in CP violation? What are the energy scales associated with the dynamics? What are the symmetries and symmetry breakings? And if there is a full Higgs sector, what is the full Higgs sector beyond the Higgs that we found and how it works? And how are the quark and lepton flavor related? In other words, how do we make a picture of all the elementary particles together? Now, in addition to that, do we have other sectors, flavor sectors accessible, for example, super partners or dark matter particles? Now, we are gathering clues from many directions, and this is how difficult problems are solved by insight and experiments in many directions. So we look for new sources of flavor breaking and CP violation in the quark sector. We determine the flavor structure of the neutrino sector, and this is a full program. We need to determine the full Higgs sector and its flavor implications. And we have discovered the Higgs initially in the boson final states, in the quark final states, and in the lepton final states. As was explained previously, there is a big program to go and also nail that. We look for non-conservation of lepton number, baryon number, and charged lepton flavor violation. In other words, everything we hold sacred, we look for the violations. And we try to find portals to the dark sector and the dark particle content, assuming that the that dark matter is a particle, which is a good assumption, but we are reaching the point that we are going to experimentally test this in direct, indirect, and collider experiments. And also we are looking for unknown physics at unknown energy scales. In fact, just 2 weeks ago, my colleagues at Caltech, Jamie Bock, who is giving a talk about BICEP, they are just going at a new scale of physics with the discovery of the B modes of the polarization of the CMB polarization. So, with respect to the scales of flavor, here is even before we started at the LHC, we had an idea from Bell and Babar, from B physics, that we can probe through the loops. We can probe scales with heavy flavor Bell, LHCb, Babar, up to 50 TeV. It was up to 20 TeV with Bell 1 and Babar, and up to 50 TeV with LHCb and Bell 2 that is coming about in a couple of years. Now, EDMs can also probe up to 1,000 TeV. Charge lepton flavor changing states can probe up to 1,000 TeV. This is mu to E, for example, but you can see here the mu to 3, the mu to 3 electrons, the conversion mu to E gamma, and the mu to E, how they probe scales here encapsulated in terms of quark masses in a plane of in a supersymmetric plane. So there is a large program to understand the flavor connection. More connections. Is the Higgs is there a Higgs portal to dark matter? What about electroweak baryogenesis? What principles stabilize the electroweak scale and creates it, of course? How does the Higgs talk to neutrinos? We know neutrinos have mass, but what is the connection with the Higgs there? What are the dynamical origins of fermion masses, mixings, and CP violations? We said that before. And extra credit with respect to dark energy and with respect to inflation. Is there a Higgs? Is the Higgs related to inflation or dark energy? And since the past week, since 2 weeks ago, March 17, when the BICEP 2 results were announced, there are tens of papers, maybe more, discussing connections of the Higgs with the CMB polarization and the possible inflation there. So the story is that we need a multi-decade global experimental effort on many, many fronts with new ideas and new technologies. The 126 Higgs, which we called initially Higgs-like, as was explained previously, what can it be still, based on the measurements that we have, is that it could be a mixture from more than one Higgs SU2 doublets signaled or SU2 triplets. A lot of these are being excluded of this scenario, but it could. It could be a mixture of CP even and CP odd states, and we're trying to do that. This is related with the angular measurements that we have, and when we arrive at the point that we have a good more data, we will be able to say more, but still now we move to precision program of measuring the full tensor structure. So could we have enhanced and suppressed couplings to photons or gluons? And the answer is yes. If there are exotic states, heavy charged or colored particles, we could have, and we're measuring this with precision again. Could the Higgs decay to exotic particles? Yes, it could. It could specifically, the dark matter portal idea is connecting it to dark matter. For the quarks and the leptons masses, we really need to measure very carefully because it may not couple to quarks and leptons precisely proportional to their masses. We're having a full program for that extends in the next decade. And also still it could be a composite without breaking the WW scattering entirety. Now, how many more Higgses could be there? Well, one of the critical targets that we are talking about for the next run that will start in a year from now, almost exactly, and beyond, is to find more Higgses, additional varieties of Higgs-like bosons, heavier, more likely. And in supersymmetry, for example, we have at least 5 kinds of Higgs bosons differing by their masses and other properties. And again, this is a joke that comes from students. Now, there was in the 70s, in fact, there was a paper by Wolfram and Politzer that discussed the Higgs vacuum instability, and the possibility was in that first paper, and also Sidney Coleman has studied it very, very much back at that time. What is this telling us is that if we put the Higgs mass on one axis and the top mass on the other axis, and we start calculating after running the renormalization group equations and after doing the beta functions, we start calculating if the vacuum is stable, yes or no. We arrive, with the current measurements, we arrive at this region, which is a metastable region. Where this is the instability and this is the stability. And the metastable region is telling you basically that in a quantum mechanical way, the universe will bubble out and arrive in a new, better, energetically favored minimum. And so that would happen in 10 to the 100 years, that would the fatal bubble will form. This was in the news. But of course, we have to be very careful when we say these things, because this assumes no new physics at all. In fact, when you put either supersymmetry or any other physics to enlarge the physics of the standard model that we know, then this plot and the calculation, of course, makes no sense. Now, the connection with ordinary matter and dark matter connections through the Higgs, well, we have seen astrophysically with observations in the sky, and this is a Bullard cluster, that the dark matter is gravitationally interacting, for sure. Anything else we go beyond that in terms of particle physics is very good educated theories and guesses, and within the standard model, the weak interactions could be giving us an interaction to the Higgs, to the dark matter particle, and the first candidate to do this was the Z. Now, if we go into super weak exchange situation, then we're talking about the Higgs boson interacting with the dark matter. And this is shown here in an old plot. I have the newest plot from Elena from the AAAS meeting, which is in the backups, but this is what Joe had in his slide. So this is the WIMP nucleon cross-section on the y-axis, and this is this weakly interacting dark matter particle mass on the x-axis. And this is the region of this exchange that I showed you in the previous slide if it was via the Z boson, and this is the region if it is via a 500 GeV Higgs. The people who are making the calculations in these plots have thought about these two regions. This is very much excluded by the experiment, but look at that. If it is via 125 GeV Higgs, the possibility of the WIMP nucleon cross-section versus mass is the sensitivity is here. The calculation is giving it here, and now the exclusion is here. So we're very close, let's say, into probing this part and have a discovery or exclusion in the next few years with the huge dark matter program that we have. Now, I'm going to talk a little bit about the so-called naturalness problem, and we were discussing this recently with Frank Wilczek, and he said to me, there's no naturalness problem. Whatever you see in nature is natural. So in terms of the Higgs, well, we have chosen to ignore the dramatic mysteries of mass in the standard model, including the Higgs, probably because well, we had fixes. I think this is why. And we didn't have the Higgs yet. That's my interpretation. And one of the first things, of course, was that if you write the Mexican hot potential, this parameter here, this M0 parameter square, is tachyonic. So when you start teaching the Higgs, the first thing that you say, oh, it's tachyonic. And then I close my eyes and I say, well, I assume electroweak symmetry breaking and everything is okay. However, well, the fact that now we have seen the particle is now going to force us to understand what is going on here. There are 20,000 papers or more related to Higgs naturalness, which is the problem of the standard model mass parameter, which has been fixed by ideas of supersymmetry. Supersymmetry we have not discovered. So it's an interesting situation we are at. The problem has to do with this one explicit mass scale of the standard model, which is this mass squared parameter, which is defining the leading order shape of the Mexican hat. Now, having not found supersymmetry, maybe one can say that we have a crisis, a quantum crisis, a SUSY crisis, whatever you want to. People get nervous about what's going to happen because without supersymmetry, we don't understand how the Higgs boson can exist without violating basic notions of quantum physics. So the fact that we have this apparent instability also of the vacuum and that we're going to tunnel away in 10 to the 100 years to some other universe is adding to the mystery. And of course, as I mentioned previously, the new discovery, the BICEP discovery, is pointing to a super high energy scale of inflation, namely the GATT scale or more. And then we talk about, then there are notions about quantum field, effective quantum field theory, and how we talk about physics. The language is very, very peculiar because we're talking about regions where you should be talking about quantum gravity. So this is a very interesting development, and the consilience, I think, will show us pointers. Now, so either the new run of the LHC should discover super partners, and I think it will, or radical new ideas are needed. And I think if we don't, yes, we will have radical new ideas. So this is the picture of the compulsory natural SUSY from NEMA. And by the way, I found the same picture with all the numbers much slower and below the W mass from 1980 something in a Savas Dimopoulos Fest. So the picture of the naturalness, natural SUSY as a solution has been there, and as we probe deeper and deeper, the picture goes higher and higher in the masses and the hierarchies. But the thing is that now we arrive at the point, we are now at the point that if we believe that indeed there is a strong naturalness argument, we must find gluinos and stops at the early LHC run. And here is a plot where it shows you the gluino mass as a function of the lightest supersymmetric particle mass on the y, and here a mass of the stop as a function of the lightest supersymmetric particle. This would be the dark matter candidate. And you see here we arrive to exclude up to 1300 almost, and here up to 650. And if I go there to this plot, you see that what he wanted there, he wanted a gluino of that, and he wanted a stop below 400. So this is the point where we have to now pause. And of course, this is the point where we have to pause and think that indeed, and at the next run, we are right around the corner, and at the next run, we will quickly have a show of supersymmetry. Now, this stranger things have happened, of course, or equally strange things that both the LEP and the Tevatron just missed discovering, and it was really around the corner. So, in other words, what this means to say is that will we be surprised if we find something just immediately after the next run starts? And the answer is no. And will we be surprised if we find nothing? And the answer is no also. So this is an interesting place to be at. So at 13 TeV, one of the nice benchmark figures that I've got here from Frank is how the cross-section, the rate of the production of this particle increases, of the supersymmetric particles. Specifically here we're talking about the gluinos, just going from 8 TeV to 14 TeV. So the increase in cross-section for a 1350 gluino is 30 times more. We will have 30 times more of this type of particles just by the increase of the energy, which is giving you again a sense about why it's so important that we probe higher and higher energies. It's a definition of high energy physics that we have to go into higher energies. And here, similarly for 750 GeV quarks, it's times 9 and so on. So we really are we're very excited about the next round. So I'm closing here, and I'm going to say that the LHC is telling us that there is mysteries. There is very important mysteries that we need to solve, and that the path towards solving them is not one and only path. We really need to consider the clues from a very huge experimental program. And I just wanted to show because recently, last week actually at Caltech, we had a visitor from Max Planck, and he discussed the Higgs amplitude states in a superfluid, strongly correlated n-body system. In fact, there are Higgs boson in condensed matter. Peter Littlewood here in Argonne and Chandra Varma, they discovered light Higgs bosons. They call them the amplitude modes on the Mexican half potential. There are also phase modes like the W's and the Z's in solids. And so these type of experiments are happening, and they're trying to describe strongly correlated n-body systems where they actually induce the production of this kind of, let's say, superfluid waves, which are Higgs amplitude modes. So from all directions of physics, we are expecting clues. Similarly, just recently there was a paper of emergent supersymmetry in topological superconductors. So maybe we will get a clue on the next steps also from condensed matter physics. And here is the importance of the mystery in the quote of Einstein. One cannot help but know when he contemplates the mysteries of eternity of life, of the marvelous structure of reality. It is enough if one tries merely to comprehend a little of this mystery every day, which is, I think, what we are all about. Thank you.
There doesn't seem to be an overall Higgs theory. Some physicists talk about one Higgs boson, others talk about 5 Higgs boson. No one ever mentions Higgsinos. My theory is that there are 64 associated supersymmetric Higgs particles, one for each matter and force particle in our universe. How do you expect to find the answer to these questions if there is no theory?
If there is no field theory, you said? If there's no theory for Higgs, you say? Sorry, I didn't hear you. Yeah, I mean, the experimental program is the experimental program, and the data is the data. So we will interpret them within what we know.
Yes. My understanding is there is no theory because some people say there's one Higgs boson, some people say there's 5. Yes. No one ever mentions Higgsinos.
Of course. What you're saying is that there is many theories.
There isn't any overall theory to answer your questions.
Yeah, well, there is an infinite space of theories and models. Beyond the 5 Higgses, there is NMSSM with an enriched Higgs sector and so on and so forth. So there are many theories, and the experiment will guide us towards which is the complete theory. But for the moment, we are looking for an extended Higgs sector because we have mysteries that are connected that could afford an extended Higgs sector.
We have to move on to another question.
I was taken by your statement, if nothing turns up at the next run at the LHC, we'll need radical, I think I heard you say we would need radical new ideas, and I just think that might be overstated. It just seems to me that there's split models around already which could easily escape detection at the next run?
Well, okay, so let me put it like that. For the experimentalists, we will always go and probe deeper and deeper. For the theorists, I think they will need some new ideas. You may not call them radical, but certainly new ideas. Otherwise, the edifice that we have built before the Higgs about how the Higgs is stabilized is not coming about. So you can remove the radical, if you like, from the point of view of theory. From the point of view of the experiment, let me put it like that. We go, we continue, we go, we probe, we shake the box and we open the box. So we do precision measurements and we do direct measurements in high energy in the frontier. We don't stop. And we try to, of course, find the connections with our cosmology and astronomy friends. Absolutely.